SwayamPrabha. Digital India. Educated India.
Hello, welcome to this lecture on biomathematics. We have been, in the last lecture we discussed about Fourier series. So, in this lecture we will continue discussing about Fourier series. So, the lecture is on Fourier series. We mentioned that a periodic function, any periodic function can be written as sums of sines and cosines. So, this is the essential idea of Fourier series which we discussed last time, and we also said that this means that any function f of x can be written as some cosine, some sine and combination of some coefficients a1, a2, a3, a4, similarly b1, b2, b3, b4 and a0. So, if you have a set of coefficients, f of x can be expanded in terms of some number times cos something else multiplied with sine. So, you can expand any function, any periodic function in this particular manner. So, what does this mean? How is it, why is it important to biology? If we think about it a bit, think of various things in biology, you can see that there are many things that repeat, like the life itself, like day to day activities kind of repeat. So, we were discussing at the beginning that there are many things in nature and in particular in a living being that is periodic. So, if you want to represent many of them, for example, concentration of many proteins depending on the time, like various cyclic, it just goes in a cyclic manner. So, they just increase, decrease, increase, decrease. So, they kind of go in a periodic fashion. Even cell cycle, in some sense the same things repeat, like the cells divide, grow, divide, grow. So, essentially there is also some kind of a periodicity, it is a periodic event again, with some particular time period, it's kind of cells keep dividing depending on the condition and so on. So, again there are different phases, and at some particular phase cells divide and then again grows, divides. So, it is also can be thought of as a periodic in mathematical language. In principle, it can be described with some kind of periodic function, some particular events in a cell cycle. For example, some concentration of a particular protein as a function of time might be increasing and decreasing in a kind of a periodic manner. So, this may not be just simple sine and cosine, cos. So, it might be a complicated periodic function, but whatever be that, however complicated that be, it can be written as a sum of sine and cosine. That is the essential message. We also know, like for example, like in the last lecture we described a function which is like this. We call this sawtooth wave. So, we describe such a function, we called it sawtooth wave. When you look at, for example, ECG or many of the machines that work in our body, like, and if you look at the signals from them sometime, various Fourier techniques are being used to analyze the signals, which we will discuss in a bit more detail in the coming lectures, where you will learn little more than Fourier series, you will learn something called Fourier transformation. At that point, it will be more interesting to discuss, but however, some kind of periodicity is again seen in some of the signals from heart or various machines that work in our body. Sometimes you might be able to find some kind of periodicity. Even if you look at the DNA sequence, like the repeat of AG or AT or GC, they might also have some kind of periodicity. So there are people have been studying whether they repeat in any kind of regular fashion, depending on in the gene region or in the intergenic regions, or we don't know, in some particular cases they do repeat in a particular manner. So even they can show some kind of a periodicity. So wherever you see some kind of a periodicity, that information can be translated into a mathematical language, and that this techniques that we use now called Fourier series and Fourier transformation can be used to study those things. So that is the bigger picture of why we are learning Fourier series and Fourier transformation. So today we will go, last time we learned sawtooth wave. Today we will learn another kind of a wave, that is the aim of today's lecture. But let us quickly remind ourselves what we discussed last time. We said that if you have a function which is a combination of sine and cos, the coefficients a n and b n can be found out by integrating that function, multiply with cosine f of x cos n x integral minus pi to plus pi will be a n, and f of x sin n x minus pi to plus pi will be b n for all values other than so the n starts from 1 to infinity, and for 0 a 0 this is just f of x dx. So this is the way we can get a n, b n and a 0, and if we know a n, b n and a 0, the function can be expanded in this particular way. So we also saw that this was the reason why we could do was this kind of a special property, that the product of sine mx and sine nx is delta mn. What does that mean is that only when m equal to n you have this 1, and all other cases this integral was 0. When m not equal to n, this integral is 0. Similarly here integral cos m cos n x dx is 0 when m not equal to n, and is equal to pi when m equal to n. Similarly here, and here this is always 0. So this integral sin m x cos n x is always 0. So this property was being used to do this, and this kind of properties can be called kind of orthogonal functions. So sin and sin m, this is, we can call it orthogonal property, orthogonal functions. So we will come back to this a bit more today later, but before that let's discuss. So last time we discussed the sawtooth wave. Today let us discuss a different kind of a wave. So let us discuss another little more extreme case. Let us discuss, just to convince you that anything can be written as a combination of sine and cos. So let us think of some function which is like this, which is repeating. So if just if you do this, right, we can call this a square wave. So we can call it a square wave. So this looks like a square. So what is it happening? So let's call this as minus pi, and this call this plus pi. Sorry, let me call this minus pi, and let me call this plus pi. Let's call this 0. So sorry, maybe I should write it a little more in a different way. So let me draw this in a different way. So let me draw this. So we can take anywhere 0 and pi, but for simplicity let me take this as this particular point as 0, this particular point as let me take this particular point as minus pi, let this particular point as 0, and this particular point as plus pi. So this is f of x, and this is x. So this is f of x, and this is your x. When x is equal to minus pi, to 0, this is a particular value, and suddenly from 0 to pi it has a different value. So, let me call this as 0, this baseline. So, from 0 to minus pi to 0, it has a value 0, and let me call this particular h value as h. H is this particular value. So, minus pi to 0, so this is minus pi. So, minus pi to 0, the value of function is 0, and suddenly from 0 to pi the value is h. So, this is, if I plot this separately here, it is a little more carefully here, it is like this. So, you have here, this is x, this is f of x, and if you mark here, so let me mark this as 0 and this as h. So, 0 till some particular point, suddenly it becomes h. So, somehow minus pi to 0, it is 0, and 0 to this particular point is pi, it is some value h. Then again it repeats. It repeats it here also. So, this kind of a square wave, how do we write this particular wave in terms of sine and cosine? Sine we know typically looks like this, something like sine. So, if I look carefully and plot it at 0, sine is 0, and at pi, so at pi by 2 it's 1, and at pi it is. So, if I just look at sine of x, it look something like this. So, where this is 0, this is pi by 2, this is pi by 2, this is pi, 3 pi by 2, 2 pi. So, similarly, if you just go from here, sine typically would look something like this. And then it comes to minus 1 and comes back here and then goes like this. So, sine with typical sine curve will look like this. So, this will be very different from So, sine wave will look like this, and square wave is very different. So, how do we make this sine to a square or a cosine to a square or a combination of sine and cosine to a square? That is the question. So, we will use the same idea. So, we use this particular idea here that if you write this particular way, a n, b n and a 0 can be found out by this formula. So, f of x, so let us define what is f of x in our case. So, for a square wave, first between minus pi and 0, when x is between minus pi and 0, f of x is 0. So, that is what it is here, that is what it is going to be here. Between minus pi and 0, f of x is 0, and it is h between 0 and pi, it is h, this particular value between 0 and pi. So, f of x equal to, look at here, f of x is equal to h between 0 and pi. So, between minus pi and 0, it is 0, between 0 and pi, it is h. H can be any value, it could be 1, 2, 3, 4, but for simplicity I will take 1 here, but you could take any particular value. So, f of x has some particular value 1 or 2 or 3, which is h for some interval, half of the interval, and the other half it is 0. So, this can be called a square wave. So, please plot this yourself and see and realize that this is indeed a square wave. Okay. So, now if you know this is f of x, as we defined previously, we can find out a n and b n, and if you know a n and b n, we can write f of x as a 0 plus sum over n is equal to 1 to infinity a n cos n x plus sum over n is equal to 1 to infinity b n sin n x. So, you can, if you know a n, even if you know b n, and if you know a 0, we can write the f of x. So, we know f of x now, because we just said that f of x is 0 for in this regime, and then it becomes 1. So, in this regime f of x 0, and in this regime f of x is 1 or h. So, if again 0, then becomes 1. So, this is your square wave. So, square wave has this particular definition for f of x. So, if we know f of x, know what we want to know? We want to calculate the coefficients. So, we want to calculate the coefficients. So, the way to calculate the coefficients is, let's look at this definition once more here. So, that according to this definition here, a n is given by 1 by pi minus pi to pi f of x cos n x dx. So, we have a n is equal to minus pi to pi f of x cos n x dx. And but f of x is 0 between. So, this I can write in two parts, that is first minus pi to 0 f of x cos n x dx, this is the first part, plus 0 to pi f of x sin n x dx. And between minus pi and 0, we know that f of x is 0. So, this whole term becomes 0, plus between 0 and pi, we know that f of x is a constant, let us call it h, which I can take outside. So, h into sin n x dx. So, what is 0 to pi sin n x dx? So, there is the overall 1 over pi here. So, there is an overall 1 over pi everywhere. So, there is a 1 over pi here. So, there is an h over pi into 0 to pi sin n x dx. So, what is 0 to pi? So, what we want to find out? What we want to find out is integral h by pi into 0 to pi sin n x dx. This is your a n. Now, what is this? Sin n x, if you plot, sin 0 is 0. So, sin 0 is 0. So, between 0 and pi, it will look like this, and minus. So, between 0 to pi, it has this particular value. So, this is h by pi into integral of sin is minus cos. So, minus cos n pi by n, nx by n in the limit 0 to pi. So, this is h by pi into minus cos n pi by n minus cos 0 is 1, and there is a minus plus, and it is 1. So, this is the answer you will get for a n. So, a n is h by pi 1 minus cos n pi by n. So, let us look what is the answer which we get here. So, a n is essentially what I wrote here, 1 over pi 0 to pi h cos nx dx. Sorry, this is Bn. Sorry, what I got here is Bn, because the sign definition is actually for Bn. So, this is actually Bn. So, there is a minor error which came here. So, let us redo this calculation. Let us redo this quickly. So, according to our definition, let us do this. So, our definition is, let us go back and check once more, because when we had made a minor mistake when we rewrote. So, the correct answer is A n is 1 over pi integral minus pi to plus pi f of x cos n x dx. Now, we know that f of x is 0, so between minus pi and 0. So, this whole thing can be written as 1 over pi into, as we said, minus pi to 0 f of x cos n x dx plus 0 to pi f of x cos n x dx. So, this part f of x between minus pi and 0, this f of x is 0. So, the whole term is 0, and the only term which is this, which is 1 over pi into integral 0 to pi f of x. F of x in the 0 to pi is a constant. So, let me call that h. So, that h can be taken out. So, this is h into cos n x dx. Now, what is cos n x for any value of n? It will between 0 and pi. So, let us plot this for n equal to 1. So, cos 0 is 1 and cos 0 is 1. So, it will just cos typically goes like this. So, this is pi. So, between 0 and there is a positive part and there is equal negative part. So, the positive part and negative part will totally will give you a 0. So, the sum between 0 and pi, this is pi, will be sum of positive and negative same numbers. So, there is an, if for any negative value there is a positive value also for each value. So, for there is plus 1, there is a minus 1, there is for each positive value there is a negative value. So, 0 to pi cos n x dx is essentially 0. So, a n is essentially 0, a n is 0. So, that is what we find. So, this is what is written here. So, a n turns out to be equal to 0 for n is 1, 2, 3 and all that. What is now B n? So, the definition of the B n is again B n is equal to integral 1 over pi minus pi to plus pi f of x sin n x dx. As we saw before, this can be written as minus pi to 0 f of x sin n x dx plus 0 to pi f of x sin n x dx. So, f of x between minus pi and plus pi, this f of x is 0. So, this whole thing is 0. So, then what you have is this. So, this is B n is essentially is equal to 0 to pi f of x sin n x dx. So, now what is 0 to pi f of x sin n x? So, f of x is essentially a constant. So, let me call this is just a constant h. So, I can take this h outside. So, what you have is essentially as B n is what we said before is h 0 to pi, there is a h by pi here, there is a 1 over pi here throughout. So, there is a 1 over pi. If you carefully do this, there is a 1 over pi, so which comes here and becomes h over pi. Then there is 0 to pi sin n x dx. So, what is integral of sin nx dx, which is minus cos nx by n, and this limit 0 to pi. So, at pi, now what is this? This is h by pi into minus cos n pi by n minus, and there is a minus sign again, and there is a plus, and 0, cos n 0 is just 1. So, this is, so basically B n turns out to be 1 minus h by pi into 1 minus cos n pi by n. So, that is what is written here. B n, if you do this carefully as we just did it, the definition is 1 over pi f of x sin n x dx, and f of x is just a constant h. You will get h by n pi into 1 minus cos n pi. This is what you will get. So, now you know that for cos n pi, for even n, when n is even, that is cos 2 pi, cos 4 pi, cos 0, cos 2 pi, 4 pi, 6 pi, they are all zeros. Sorry, they are 1. Cos 0 is 1, cos 2 pi is 1, cos 4 pi is 1. So, cos n pi when n is even number 0, 2, 4, this is 1. So, this is 1 minus 1 is 0. So, B n is equal to 0 for n when n is even. For n even, B n is 0. For n odd, B n is 2 h by n pi, because when n odd, this is essentially minus 1, cos n pi is minus 1 for n odd. So, 1 minus minus 1 is 2, 1 minus minus 1 is 2. So, this is essentially 2 h by n pi. So, B n is 2 h by n pi when n is odd, and B n is 0 when n is even. So, that is the case here. Now, what we want? We want a 0. What is a 0? So, a 0 is just minus pi to pi f of x dx. So, f of x is a constant. So, minus pi to pi, in this case it is h. So, this is just simple this. So, dx is x, and this is h into pi minus pi is like 2 pi. So, this is essentially there is a 1 over pi here. So, there is a 1 over pi everywhere. So, there is a 1 over pi here. So, there is a pi h by pi into pi. So, essentially pi. So, this is again only from 0 to pi. So, this can be again written as 0 to pi f of x dx plus minus pi to 0 f of x dx, and this is 0 because minus pi to pi f of x dx as we just saw is 0. So, this is only from 0 to pi. So, essentially this will come as pi. So, this and this pi cancels, the answer is h. So, a 0 is h, and our series is f of x is a 0 by 2 plus sum over n is equal to 1 to infinity a n cos n x plus sum over n is equal to 1 to infinity b n sin n x. So, now what did we find? We found that a 0 is just h. So, a 0 first term was just h by 2, one term was just h by 2. We found that a n is 0. So, the whole thing is 0, and b n is, we just saw that b n is 2 h by only for n equal to odd it is a non-zero value, for all even value is just a 0. So, this is again the sum, this particular term b n is only non-zero for odd values of n. So, that means when n is equal to 1, 3, 5, this is non-zero, everywhere else it is 0. So, essentially what happens is that essentially you end up, if you do this carefully, you end up with this particular formula. The series for a square wave is that f of x is equal to h by 2, which is a 0 by 2, times 2 h by pi into sin 1 x by 1 plus sin 3 x by 3 plus sin 5 x by 5 plus dot dot dot, so on and so forth. So, what does this? This is a is 0. So, this is b, as we rightly saw. B was basically 2 h 2 by n pi. So, it's 2 by pi is taken out, and 1 over n is here, this is 135, and we found that this is only true for an odd value. So, we only have odd values here. So, if you apply all this together, you end up this series. So, this should represent a square wave. H by 2 plus 2 h by pi into sin x by 1 plus sin 3 x by 3 plus sin 5 x by 5 plus so on and so forth should give you like a square wave. Do you think it will give a square wave? Let us check. So, let us, for simplicity, what is just f of x is just h by the first term alone. If you look at here, the first term alone is one term is just h by 2. So, h by 2 is anyway, we know that if you just plot h by 2 f of x, it is not surely a square wave. H by 2 is just a line. So, let us take h as 1. So, this is just a line passing through half. This is h by 2. So, the first term alone will not give anything. So, this first term in the sine series, can it give you something? So, let us look at this first term, that is sin x by 1. Can it give anything? So, let us look at, so this is just h by 2. Now, if add the first term, which is 2 h by pi into sin x by 1. What does that look like? So, that is what is shown here. If you look at the first term alone, what you have is that h by 2 plus 2 h by pi into sin 1 x by 1. So, that is the first term, and you can see that if you plot this, you pretty much get a sine wave, because this is sine plus some constant. So, it is just a bit of a shifted sine wave, shifted by a small value maybe. So, this is just a shifted sine wave. As you can see, this is just a sine wave shifted from some particular value to some other value. So, you can see this here. So, first term alone, this is not surely like a square wave. Now, let us look at another term, which is the second term, add one more term to this. So, if we add one more term, what happens? H by 2 plus 2 h by pi plus sin x by 1 plus sin 3 x by 3. So, this is the new term that we added. It has changed its shape quite a bit, but it surely is not yet a square wave, but it is slowly, just some shift has happened. So, we added two terms. So, this is this term plus this term, plus of course, this term is a constant we are not considering. So, there are two sine terms essentially. Now, let us add one more term, 3 terms in the series. It is slightly better. So, as you can see, it is just coming, the shape of a square is about to come, it is just starting to come. Even after just 3 terms, you can see that the square is begin to emerge, even though it is far from a square. So, the f of x of this is essentially h by 2 plus 2 h by pi plus sin 1 x by 1 plus sin 3 x by 3 plus sin 5 x by 5. So, you can see that this interesting combination of signs gives you very interesting like a function, which is not very easy to intuitively think that you will get this. Add one more, sin 1 x by 1 plus sin 3 x by 3 plus sin 5 x by 5 plus sin 7 x by 7, 4 terms. Then you get a better, is more approaching towards a square. So, there are 4 terms and it's somewhat is actually nearer to square, and then you add one more term and you have something which is little more closer to a square. So, look at, there is sine 1x by 1, there is sine 3x by 3, there is sine 5x by 5, sine 7x by 7, sine 9x by 9. So, essentially you have 1, 2, 3, 4, 5 terms inside this bracket, essentially 5 plus 1 constant term. So, essentially 5 terms which is x dependent terms, and that gives somewhat closer to a square, but actually far from square. But however, this seemed to look like it is very far from sine, it is more like a square wave. So, now if you add more and more terms, as this goes 9, as you add 11, 13, 15, 17, and as you go to infinity, this will become a perfect square wave. So, that is the idea. But it is intuitively, before we writing down these principles, one wouldn't think that by just adding some set of sine, you will get a square. This is very difficult to think of, but and given that sine can be made to a square, or a combination of sine and cos can be made square, rectangle, sawtooth, any shape can be constructed, any periodic function can be constructed as a combination of sine and cosine. So, essentially that is the message this gives. We just saw that there are, with 5 terms you get pretty good decent square, as you see here. So, if you have 5 terms you get pretty decent square looking, this is somewhat looks like a square wave. So, we need at least 5 terms, and if you add more and more terms, it becomes like a perfect square wave. So, now let us see a movie of how more and more terms makes it better square. So, this is, we are moving up 1 term, 2 terms, 3 terms, 4 terms, 5 terms. So, 1 term, 2 term, 3 term, 4 term, 5 term, 1 term, 2 terms, 3 terms, 4 terms, 5 terms. So, when you have 5 terms, as you can see in this movie, just let us see the movie here. So, as you can see in this movie, the more and more terms, it becomes more and more square. So, the movie is repeating. Let us watch it for a minute. So, 1, 2, 3, 4, 5. So, the more and more terms, it becomes more and more square shape. So, this is the essentially how the Fourier series, the infinite series, the more and more terms you add, it becomes like a square wave. So, essentially you can make the square wave by summing sine 1x by x plus sine 2x by 2x plus sine 3x by 3x plus so on and so forth. Sorry, sine x by x plus sine 3x by x 3x plus sine 5x by 5 plus, so essentially, sorry for the, so this is essentially the series sine x by 1 plus sine 3x by 3, sine 5x by 5 plus sine 7x by 7 plus sine 9x by 9 plus sine 11x by 11 plus sine 13x by 13 and so on and so forth, will generate a better square wave, a good square wave. Okay, so we saw that sawtooth wave and square wave, how do we generate it? Now, any function you can generate in this particular manner, and one of the property that we, so as we said, we have the square wave as we generate from the series of sines, and one of the property that we used to write this Fourier tree, some important property is this property that we saw, that if you multiply sin mx and sin nx and integrate, you get 0 or 1 delta function, something called Kronecker delta, which we discussed, and cos and cos you get again Kronecker delta, and cos and sine you get this. So, this kind of a property wherever this, we saw that for when we also said that, we also briefly said that whenever you write a vector A as A I plus B j plus C k, this I dot j is 0, I dot I is 1. So, this kind of orthogonal relationship was needed to write this, expand this in a series. So, but there is an interesting another set of functions like which is related to cos and sine is also can be used to expand the Fourier series, which is all these orthogonal properties. So, you know that it can be read e power I n x. You might know that this can be written as cos n x plus I sin n x. So, cos x plus I sin n x is e power I n x, and integral e power I n x into e power I m x dx minus infinity to infinity. This is basically integral minus infinity to infinity n plus m. So, this is e power I into n plus m, n plus m plus n into x dx. So, what is this? What is the answer to this? What is an integral of integral e power I into some constant times x? So, it turns out that integral minus infinity to infinity e power I k x, where k is some number which is m plus n, can be written as 0 if k is not 0. If k is not 0, e power I k x can be written as cos k x plus I sin k x, and as you know, cos and sine will be like periodic functions like this, and if you go from minus infinity to infinity, the sum area under this will be 0, because this is a positive part, there is a negative part, positive part, negative part. So, for each positive part there will be a negative part. So, minus infinity to infinity, this cos and sine will, positive part and negative part will cancel each other. So, this will give you 0. So, whenever there is a k, non-zero k, it is like a wave, and whenever is a wave, minus a periodic wave, minus infinity to infinity, the integral will be 0. So, this is 0 if k is 0, and this is not 0 if k is 0. If k is 0, integral e power I k x minus infinity to infinity is basically e power I into this is 1 and this is dx. So, this is basically essentially you will end up as infinity. So, this is 0 if k is 0, infinity if 0 if k is not 0, integral of e power I k x is 0 if k is 0, integral of e power I k x is infinity if k equal to 0. If k is equal to 0 is essentially integral dx. Integral dx is just x, and x at infinity is infinity, and infinity minus infinity is essentially 2 infinity, which is essentially infinity itself. So, this is infinity. So, such property, such function can be written as something called the Dirac delta function. Dirac delta function is a function which is infinity only at k equal to 0, and for all values of k So, this I can write delta of k, this is written as delta of k. Delta of k has a value only at k equals 0 is infinity, everywhere else it is 0, and integral minus infinity to infinity delta of k dk is 1. So, essentially any function which has only value at just one point and everywhere else is 0. So, this is f of x and this is x, only at x equals 0 it is a value, everywhere else it is 0, then this function f of x can be called as a Dirac delta function, which is delta of x. So, what we are saying is that integral minus infinity to infinity e power I k x dx is essentially a delta of x, sorry, delta of k. When k is, so this is delta of k. When k is 0, this is infinity. When delta is k is non-zero, it will have value. It will be 0. So, this is so similarly. So, this is somewhat similar to what is here. Somewhat very similar to what you have here. So, based on this property, one can write. So, based on this property, one can write f of x as one can expand f of x in terms of e power I n x also. So, what we said previously is that one can expand any periodic function in terms of sines and cosines. Here we are saying little more. We are saying a periodic function f of x can be expanded in terms of e power I n x with some coefficient c n, and where n goes from minus infinity to infinity. So, the same thing we are saying in a different way. We need not have e power cos x and sin x. Future e power I n x is also can be used to expand this. So, any x function can be written as a sum of e power I n x. So, that is what essentially this is saying. Any function, periodic function f of x can be written as n minus infinity to infinity sum over n minus infinity to infinity c n e power I n x. So, how is c n and the previously a n and b n, how are they related? They are related. C n is essentially can be obtained just like previously we used to do. F of x into e power minus I n x dx is c n, and the c n's are related to a n and b n in this particular way. So, either you know, if you know c n, you can calculate a n and b n. If you know c n, so this is the relation for all a n and b n. So, essentially what we are saying here is that series, any function, any periodic function either can be written as f of x can be written as a 0 by 2 plus sum over n is equal to 1 to infinity a n cos n x plus sum over n is equal to 1 to infinity b n sin n x, or f of x can be written as sum over n minus infinity to infinity c n e power I n x. So, both are possible, and you can calculate a n b n in that case. So, this is same thing, either at the top or bottom. We can use one of this way, one way to write a periodic function, expand a periodic function in terms of an infinite series, and any function that we see in biology pretty much, sorry, many periodic functions that we see in biology can be learned and understood and used using this particular series. So, this is the techniques of Fourier series. Now, we will extend this to something called Fourier transformation, and this Fourier transformation is highly powerful, both to understand many things and also to even to solve some differential equations. We saw that differential equations are very important in biology, So, this Fourier transformation, which is kind of an extension of this to a general case, and some are related to Fourier series. This can be again used to understand many problems in mathematics in general, and essentially mathematics related to biology. So, with this we will stop today's lecture. So, we discussed today another example of Fourier series, square wave, and exponential, the way of expanding Fourier series using an exponential function e power I n x. So, with this I will stop today's lecture. Bye.